Good evening everyone, good evening elites. Welcome back again to the NEET Elite. I hope you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone, yeah? Just give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys or not. Right? Hello Jaya, hello Aparna. Hello Afshan, hi Raja, hi Gayatri, hello Farooq, hi Arzu, hi Shweta. Hello Ashwarya. Well people, just let me know in the chat box if I'm audible and visible to everyone or not, yes? Hello Pooja, hello Albert, Asifa, Afshan, Samiksha, welcome everyone, welcome. Welcome back to your NEET Elite. So people, as you all must be knowing, today we are going to start the new chapter from your organic chemistry part, from your class 12th organic chemistry, and this is what we call as haloalkanes and haloarenes, yeah? Okay, so before starting the session, for the ones who are new to the channel, let me introduce myself. My name is Wassim Sir and I'm your chemistry master teacher writer on this NEET Elite channel, yeah? The ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well, right? Do like the video, share the video with your friends, and do not forget to subscribe to the channel as well, and do not forget to hit the bell icon so that you get the notification of every single session which will be taking live on this NEET Elite channel, yeah? Well, Sai Das is new to the channel. Welcome to the channel. Hello Karthik, how are you? Perfect guys. It's okay Gayatri, it's okay, no issues at all, yeah? Okay, so people, let me know in the chat box if you guys are super duper excited about the session, right? Let me know in the chat box, fast. Well, let me tell you, in the today's session, we are going to talk about something called as Sn1 reactions, mechanism of Sn1 reactions, the factors that affect the Sn1 reactions, and this topic, stereochemistry of Sn1 reactions. This is not something which I'll be teaching you today, okay? I'll be taking a separate session in which I'll be discussing the stereochemistry of Sn1 as well as Sn2 together, yeah? So basically in the today's session, these three topics we are going to cover right here, okay? So let me know in the chat box if you guys are super duper excited so that I can start the session directly without wasting a lot of your time, yeah? So we are going to learn the nucleophilic substitution reactions, Sn1 reactions we are going to talk about in the today's session, yeah? Perfect. So let's get going. Let's get started with something called as Sn1 reactions. Okay. First of all, what are these Sn1 reactions all about? Sn1 stands for unimolecular nucleophilic substitution reactions. Unimolecular nucleophilic substitution reactions. Okay. So what are these Sn1 reactions? First of all, let me tell you, these are the reactions in which rate of the reaction varies linearly with the molar concentration of the substrate. Sn1 reactions, your unimolecular nucleophilic substitution reactions, these are the ones in which the rate of the reaction varies linearly with the molar concentration of the substrate. Point number one, right? So I'm writing it over here, I'm mentioning it, and I'll make you understand this in some time, okay? In these reactions, you can say the rate of the reaction varies linearly with the molar concentration of substrate. Point number one, right? So people, if the rate of reaction is varying linearly with the molar concentration of substrate, then simply I can write the rate law as, I can say rate of this Sn1 reaction, it's directly proportional to the molar concentration of substrate raised to the power order, and it is a first order reaction, so the power over here is 1, okay? Or you can write it like this, R is equal to K multiplied by concentration, which is basically the molar concentration of substrate raised to the power 1. This is how we write the rate law for this Sn1 reaction. Okay, you can clearly see the rate of the reaction is varying linearly with the molar concentration of substrate over here. Yeah? Okay. Now people, let's try to understand about this nucleophilic substitution reactions, about Sn1 reactions a bit more in detail. First of all, let me tell you, these Sn1 reactions, these are basically the first order reactions. Their order is 1, right? And at the same time, let me tell you, Sn1 reactions, these are unimolecular in nature, right? Their molecularity is equal to 1, right? That's why I'm calling these are unimolecular reactions. Few points which I want every one of you to take a note of. In case of Sn1 reactions, in case of unimolecular nucleophilic substitution reactions, the rate of the reaction varies linearly with the molar concentration of substrate, point number 1. Rate of the reaction is equal to a rate constant multiplied by molar concentration of substrate raised to power 1. This Sn1, it is the first order reaction, and at the same time, its molecularity is 1. That means it's unimolecular in nature. Yeah? Let me tell you, this Sn1 reaction, right? This Sn1 reaction, it's completed in 3 steps. In books, you can find it written like this as well. You can see it's, in some books, you can find it Sn1 reactions are completed in 2 steps, right? But you should remember, it gets completed in 3 steps. And what are those steps going to be, right? What are those 3 steps going to be? We are going to talk about those steps in detail. Remember, your Sn1 reactions, they get completed actually in 3 steps, right? Okay. First of all, those reactions in which the rate of reaction varies linearly with the concentration of substrate, point number 1, right, which I've told you. This is how we write the rate law for this Sn1 reaction, point number 2. Point number 3, the order of this reaction is 1. It is a unimolecular reaction, and this Sn1 reaction gets completed in 3 steps. Now the point is, what are those 3 steps? What are those 3 steps in which the Sn1 reaction gets completed? Okay. Well, the step number 1 is the ionization step, or we call it as the formation of carbocation step. In the first step, we always get the carbocation, right? Or that step in which carbocation will be getting generated, that's what we call as ionization step as well. Okay, the first step is the ionization step, right? The second step is the formation of protonated alcohol, which I'll be showing you in some time. And the last step is the formation of alcohol, or I can say directly the formation of product. Now let's talk about these steps in detail over here, yeah? Let's get going, let's get started. See guys, understand. First of all, this is one tertiary alkyl halide which I've taken over here. As you can see right here, this X is basically the halogen. This X is basically the halogen, right? It is the tertiary alkyl halide over here, right? Okay. Now, first of all, in water, what is going to happen? In water, what is going to happen? First of all, this water over here, it's a solvent, right? It is a polar protic solvent. Its dielectric constant is very high, right? It's a polar protic solvent with high dielectric constant, as you all must be knowing. Yeah, point number 1. Now, what is going to happen to this tertiary alkyl halide when I'll put it into water? First of all, what is going to happen? This bond, it gets broken down, right? Or you can say this X leaves as X negative, due to which this carbocation is formed over here, due to which there will be positive charge on this carbon over here, right? So if X leaves as X negative, right, there will be the positive charge which will be getting created on this carbon. So you get the carbocation like this. This is CH3, this is CH3, this is CH3, and you get a positive charge over here. So in the first step, breaking of bonds takes place, right? In the first step, ionization happens. In the first step, carbocation gets formed, right? So remember, the first step, which is basically the ionization step, which is the formation of carbocation step, it is basically the slowest step of this Sn1 reaction. So this step right here is the rate determining step. This is basically the rate determining step in case of Sn1 reactions, correct? Okay. Now people, in the first step, carbocation gets formed. Now what happens in the second step? The carbocation which gets formed in the first reaction, what happens to this? Okay. Now this solvent which I've taken over here, in this case I've taken the solvent as water. Okay. This water, it has got 2 lone pairs on this oxygen. This water is going to act like the nucleophile right here. Okay. What is the nucleophile? Nucleophile is something which we call as nucleus loving species. Okay. So this water right now, it's going to act as the nucleophile. Since this carbon is the electron deficient center, so this water is going to attack at this carbon, right? This water, the lone pair of the oxygen is going to attack at this electron deficient center, due to which you get something called as protonated alcohol, yeah? You get something like this. This is CH3, this is CH3, right? And with this carbon, OH2 gets attached like this. This is your OH2 and there will be a positive charge on this oxygen over here. And what do we call this substance over here? This is something which I call as protonated alcohol. This is what I call as protonated alcohol, right? Now people, since you got the protonated alcohol, okay, now the protonated alcohol which gets formed in the second step, which is this one, this is C, this is CH3, and with this carbon you have got CH3 attached, and with this you have got OH2 attached as well with a positive charge on oxygen, right? This is the protonated alcohol. Now this protonated alcohol, what it does exactly is, okay, in water, this water right now, it's going to act like a base now, okay? Over here, this water was acting as the nucleophile. Right now, the water will be acting like a base. So it's going to abstract the H positive among these two. It's going to take any one of the hydrogen out of these two, right? Okay. Now, we will understand what is going to happen. See, first of all, you can say it like this as well. Since the oxygen got positive charge right here, positive charge on an electronegative element makes it more electronegative, due to which one of this bond will be broken down towards oxygen, right? One of this bond will be broken down towards oxygen and hydrogen is going to leave as H positive, and basically actually it is this water which takes this H positive out from here, right? So what do you get the product as? You get the product something like this. This is CH3, this is C, this is CH3, this is one more CH3, and with this CH3 OH gets attached, and finally you get something called as alcohol as the product in this case, yeah? Let me know in the chat box if it is clear. First of all, let me give you the quick overview of all this again. What happens in the first step? In the first step, your alkyl halide, right? Okay, the bond between this carbon and this halogen, it gets broken down towards halogen, due to which this halogen X, it leaves as X negative, as you can see right here. This halogen leaves as X negative, due to which there will be a positive charge on this carbon. So basically, a carbocation got generated over here. A carbocation got generated in the first step, which is what I call as the ionization step. In the second step, what is going to happen? This carbocation, right, nucleophile is going to attack at this carbocation, right? Now the nucleophile, it can be the internal nucleophile, it can be the external nucleophile. If the solvent is acting as a nucleophile, we call this nucleophile as the internal nucleophile, right? And if the solvent acts as the nucleophile, this process is also called as solvolysis then as well, okay? When the solvent acts as a nucleophile, we call this step as the solvolysis as well, due to which lone pair of this oxygen attacks at this carbon deficiency, electron deficient center, right? So what do you get over here? You get the protonated alcohol. This protonated alcohol, what happens in this protonated alcohol? The water which is already in the container, that takes H positive out, due to which one of the bond between oxygen and hydrogen is broken down towards oxygen, due to which this positive charge gets compensated and hydrogen leaves as H positive, and that H positive is basically taken by this water. Okay, so finally you get an alcohol like this over here as the product, right? So in how many steps this reaction has taken place? It has taken place in 3 steps, right? Out of 3 steps, which one is the slowest step? This one is the slowest step. So your ionization step in case of your Sn1 is going to be your rate determined step, yeah? Okay, as simple as that, right? Now people, let's move on. Let's talk about a few more things. This is something which I've told you. This water is going to take this H positive out, so you get the alcohol as the product in this case, right? Okay. Now people, what happens over here? There is one important statement which I have mentioned over here. See, since the intermediate of this reaction is carbocation, right? The intermediate of this reaction is carbocation, right? And therefore, rearrangement of carbocation is possible in this Sn1 reactions, okay? So in the first case, basically what happens due to the ionization, your carbocation got formed, right? So your carbocation is the intermediate, and we know in case of carbocation, rearrangements are possible. For example, 1,2-methyl shift is possible, 1,2-hydride shift is possible, right? And remember, rearrangement of carbocation will only take place if due to rearrangement, stability of carbocation increases. If due to the rearrangement stability of carbocation increases, then only rearrangement takes place. If the stability of carbocation does not increases, okay, if the stability of carbocation does not increase at all due to rearrangement, then that rearrangement does not happen. So remember, rearrangement will take place only if the stability of carbocation increases during rearrangement, right? Due to rearrangement, correct? I'll be giving you the examples one by one. With those examples, all the concepts will get properly clear. I'm sure about that, yeah? Let's move on. Let's start with a simple question. By solving this question, you'll get the clear-cut idea of how your product is going to get formed, yeah? Okay, right? See guys, over here I have taken an alkyl halide, yeah? This is basically your alkyl halide. This is your halogen attached with the carbon, right? Now, what am I going to do? I'm going to show you the Sn1 mechanism over here, and the solvent which I've taken is again the polar protic solvent, that is water, right? So first step, what you guys are going to do over here is, you guys are going to break this carbon-halogen bond, okay? Assume this, what is going to happen over here is basically this halogen, it takes the electron pair with itself, or I can say this X leaves as X negative, due to which there will be positive charge on this carbon. So when we broke the bond between carbon and halogen, the positive charge got created on this carbon, right? So you got something as, this is CH3. On this carbon, you got the positive charge. On this carbon, you got the positive charge. Rest, everything is the same. This is CH2, this is CH2, and with this CH2, you get CH3 as well, okay? And since this is the first step, which is the ionization step, right, in which the carbocation gets formed, and first step is reversible in nature, we know it, and it is basically the slowest step, so it is again going to be your rate determining step over here in this case as well, yeah? Okay, now we will understand. This is the carbocation which gets formed over here. First of all, we know carbocations are stabilized by hyperconjugation, right? Carbocations are stabilized by hyperconjugation. See, this is the carbon carrying the positive charge, right? The other carbons which will be attached with this carbon, those are what I call as alpha carbons. And the hydrogens which are attached with these alpha carbons, those are what I call as alpha hydrogens. So how many alpha hydrogens do we have right here? 3 plus 2. We have got basically 5 alpha hydrogens which are stabilizing this carbocation over here. Okay. So first of all, once the carbocation gets formed, now I'll check, will there be any sort of rearrangement over here or not? Okay. Let's understand. Let's try to understand. Let's see if there will be any sort of rearrangement over here or not. Okay. Understand properly what I'm going to see. What I'm going to do. Okay. First of all, this carbocation, it's stabilized by how many alpha hydrogens? It's stabilizing by 5 alpha hydrogens, right? See, I'm going to make this carbocation again like this. This is CH3, for example. This is CH with a positive charge right here. And this is CH2, correct? I'm going to make one bond over here like this. Yeah. And you get CH2, CH3, correct? Yeah. Let's call this carbon as carbon number 1. Let's call this as carbon number 2. If hydrogen leaves as H negative, and that H negative gets attached at this position, the positive charge will shift from here to here then, yeah? We know it. So the second carbocation which gets formed due to rearrangement, it's going to be like this. It's going to be CH2, this is going to be CH with a positive charge over here on this carbon, and you get CH2, CH3 as such, okay? Now people, see, if this rearrangement happens, this is basically your 1,2 hydride shift. This is 1,2 hydride shift which I'm doing over here, correct? Now people, if this is the carbocation now, how many alpha hydrogens it has? 2 and 2, 4. So this carbocation is getting stabilized by 4 alpha hydrogens, right? There is one more possibility. If I would have done 1,2 methyl shift over here, right? Okay. There is one more possibility. There is one more possibility in this case. Again, I'm going to make this carbocation over here. It's going to be CH3. It's going to be CH3. This is your CH with a positive charge. I'm going to make this carbocation again, right? That means this carbocation, right? And this is your CH2, this is CH2, and this is CH3. There is one more shift possible. There is one more rearrangement possible over here. What is that going to be? See, just have a look. This is your what? This is your CH3 over here, okay? First of all, if you take H negative out from here and you are going to attach that H negative with this, so the positive charge comes on this carbon, right? See, this is basically your CH2, correct? You can write it like this. This is CH2, with this you have got one hydrogen attached, right? If hydrogen leaves as H negative, that H negative gets attached at this carbon, this positive charge gets shifted at this carbon, right? And if that happens, what is the carbocation which I'm getting after the rearrangement? It is going to be simply CH2 with a positive charge, right? And this is going to be CH2, this is going to be CH2, this is going to be CH2, this is going to be CH3. This is one more carbocation which gets formed right here. Okay, so this carbocation, it's getting stabilized by only 2 alpha hydrogens, right? So how many carbocations we have right now in this case? So this is the first carbocation, right? This is the second carbocation. Yeah, this is the third carbocation. Now see which carbocation is the most stable. The first one is the maximum stable because it's getting stabilized by maximum alpha hydrogens, right? So I'm not going to do any sort of rearrangement over here because the rearrangement I'm going to do only if due to rearrangement stability of carbocation happens, okay? If stability of carbocation increases. But due to the rearrangement, stability of carbocation is not increasing, right? So I'm not going to do any sort of rearrangement over here. Point number 1, okay? Now, I'm going to deal with my first carbocation only, right? So I hope you got this phenomenon right here. Now people, this is the carbocation which I got. Now what happens to this carbocation? See guys, the carbocation is something like this. This is CH with a positive charge over here. This is CH2. This is again CH2. And with this CH2 you have got CH3 attached as well, right? This is the carbocation which I have, which is getting stabilized by maximum alpha hydrogens. Now what is going to happen? Understand. Now people, what this water is going to act like, this water will be acting like a nucleophile. Nucleophile is something which we call as nucleus loving species, right? So the lone pair of oxygen is going to attack at this position. And when the lone pair of oxygen will attack at this position, what do you get over here? You get CH3, right? You get CH3 as such. This will be CH, and with this CH, what do we have? We have got OH2 positive attached as well. This oxygen, with this oxygen, you have got 2 hydrogens like this, and there is positive charge on this oxygen, correct? Rest, everything is same. This is CH2, this is CH2, and this is CH3, right? Now, people, after this, I got something as, we call this as protonated alcohol, if you remember, yeah? This is something which we call as protonated alcohol, right? Is this solvolysis which has happened over here? Right now, currently, the water has act like the nucleophile, right? The solvent has act like the nucleophile, right? Okay, since when the solvent acts as the nucleophile, that step is what we call as solvolysis. So this is the solvolysis step over here, right? Now, what is going to happen after this? This protonated alcohol which I got over here, what is going to happen to this? I'm going to show it over here only. I'm going to show it over here only. Now in presence of water, this water will be acting like a base, and it's going to abstract this H positive from here, right? It's going to take this hydrogen out as H positive. When can this water take this hydrogen out as H positive? When the bond between oxygen and hydrogen gets broken down towards oxygen. So what is the final major product which you got over here? It's going to be CH3. It's going to be CH3. This is CH, and with this CH you have got OH attached, and right here you got CH2, this is CH2, and this is CH3. So this is the major product which I got in this case, right? I'm sure it's clear to everyone. Yeah? Right? Just give me some thumbs ups in the chat box if you got to know, right? Let me know if it's clear to everyone or not. This is the product which I got at the end. I've got few more examples. By doing those examples, everything will be getting clear to you one by one. Yeah? There are a lot of concepts which we are going to deal in the today's session. So this is something which we have done, right? This is something which you'll be getting in the Telegram group in the form of PDF, yeah? Now people, moving on to one more. Understand this properly, okay? Understand this properly. First of all, this is the halogen. It is attached with this carbon basically, right? So what is the first step which we do? We have to show you, I need to show you the Sn1 mechanism. So break this bond, right? X leaves as X negative, so that there'll be positive charge on this carbon. So this is the carbocation which got formed over here. This is carbon, this is CH3, this is one more CH3, this is one more CH3, right? And you get something as CH2 with a positive charge over here, correct? Since carbocation got generated, now I need to check, will the rearrangement going to take place over here or not? Is the rearrangement going to happen over here in this carbocation or not? We are going to see that, okay? If due to rearrangement, stability of carbocation increases, then only rearrangement will happen. Okay. Now people, let's call this as carbon number 1. Let's call this as carbon number 2. Now what I'll be doing over here is I'm going to do 1,2 methyl shift. I'm going to do 1,2 methyl shift, right? I'm going to take this CH3 negative out from here, and that CH3 negative will be getting attached with this CH2, and the positive charge finally comes at this carbon, right? So how do I represent it now? It's going to be CH3, there is a positive charge on this carbon, right? And this is your CH3 over here in this case, and this is going to be your CH2. With this CH2, you are going to attach this CH3 over here, right? As simple as that. Now people have a look. In this carbocation, how many alpha hydrogen? I mean, you can clearly tell me. See, this is 1 degree carbocation. This is 3 degree carbocation. 3 degree carbocation is definitely more stable. Yeah. Yes. 3 degree carbocation is definitely more stable than that of 1 degree carbocation. Yeah. So due to rearrangement, what's happening over here? Due to rearrangement, stability of carbocation is increasing, right? Now, since the stability of carbocation has increased, so rearrangement will happen over here. Now, after this rearrangement, what is going to happen? The nucleophile, that is your solvent, that is your water, that's going to attack at this position over here. Yeah? Okay. So, you have got the carbocation like this. This is CH3. This is C with a positive charge, right? C with a positive charge. And on the top, you have got CH3, right? And what do we have? Apart from this, you have got CH2 and CH3 as well, right? Now people, after this, what is going to happen over here? As I told you, your water solvolysis is going to take place over here. Lone pair of oxygen is going to attack at this position. So you get the protonated alcohol over here, right? You get the protonated alcohol over here. This is C, this is CH3. And with this carbon, OH2 gets attached like this with a positive charge on this oxygen, right? And over here, you'll be simply writing CH2, CH3 as such, correct? Now, what is the next step which is going to happen after this? What is the next step which will be happening after this? What is the next step? Again, this water, the water which is my solvent, now it's going to act like the base. It's going to take hydrogen out from here as H positive. And if hydrogen leaves as H positive, that means this bond will be broken down towards this oxygen. So what is the final product which you get over here? The final product and the major product, I must say, it's going to be CH3 on the top. Right? You have got OH over here attached, and with this you have got CH2, CH3 as well. Correct? This is the major product which I got in this case. Just let me know in the chat box if everything is clear till here so that I can move on to the next one, yeah? Let me know fast in the chat box with some thumbs ups. Let me know in the chat box with some thumbs ups if it's clear to everyone or not, yeah? Right. Perfecto. Wonderful. Okay. Let's move on. Let's get going with one more example, yeah? This is something which we have done in this case, okay? So, let's move on and let's see what is going to be the product in this case. See, again we have got what? Again we have got alkyl halide, right? I'm going to show you the Sn1 mechanism again, and the solvent which I have taken over here, that's water, correct? Now people, what is going to happen over here? First of all, you are going to break this bond, right? So that will be a positive charge on this carbon, right? Okay. The first step leads to the formation of carbocation, and the carbocation over here is going to be CH3. This is CH3 attached on the top, this is hydrogen, and on this side you have got CH2 positive as well. Now, since the carbocation is formed, now is there any chance of rearrangement? See, right now it's 1 degree carbocation, right? If 1 degree carbocation somehow gets converted into 2 degree or 3 degree carbocation, then only rearrangement is going to happen, yeah? Now people, over here, let's call this as carbon number 1, let's call this as carbon number 2. If this hydrogen leaves as H negative and gets attached with this CH2, this positive charge will eventually come on this carbon, right? So, due to 1,2 hydride shift, I'm getting a more stable carbocation. I'm getting a tertiary carbocation, yeah? It's going to be CH3. There'll be positive charge on this carbon, and with this carbon, you have got CH3 attached, right? And you'll be getting something as CH3 over here as well, right? I'm sure it's clear till here. Now we will understand. This was 1 degree carbocation, this is 3 degree carbocation. Absolutely, your 3 degree carbocation is more stable. We know it, yeah? Now people, see, what your solvent, water is going to do over here, it's going to act as a nucleophile, and this lone pair of oxygen is going to attack at this position. And when the lone pair of oxygen attacks at this position, I'm now going to make a final product. I'm not going to show you both the steps. I'm finally making you the final product, right? The final product over here is going to be CH3. This is C. With the CH3, I've got CH3 attached on the top. You'll be getting OH over here. You'll be getting CH3 as the final major product, right? As simple as that. Okay. People, basically over here, when this water attacks as the nucleophile, you get the protonated alcohol, which I've shown you in the beginning, protonated alcohol. From that protonated alcohol, H positive is taken out by the water, and finally you get this as the result, okay? I'm sure it's again clear to everyone, yeah? This was one more case in which 1,2 hydride shift has taken place, okay? Right. Perfecto. Let's move on to one more example. Let me show you a few more important examples. People, this is one important example, okay? If you remember, your in case of E1 reactions, I've taught you in hydrocarbons, if you remember, right? Right? Same thing is happening over here in Sn1 as well, yeah? So people, what happens in this case? First of all, again, Sn1 mechanism, break this bond, right? There will be a positive charge on this carbon, so your carbocation is like this. This is your carbocation, CH2 with a positive charge, correct? This is your carbocation, right? And first step is the ionization step, and it's reversible, and is the slowest step as well, we know it. Remember, whenever carbocation will be attached with a ring, whenever carbocation will be attached with a 4-membered ring, 5-membered ring, 7-membered ring, okay, at that time ring expansion takes place. If you remember, I have taught you this in E1 mechanism as well. Whenever carbocation is attached with the 4-membered ring or 5-membered ring or 7-membered ring, at that time what happens? At that time ring expansion happens, okay? Now how this ring expansion over here takes place? A ring expansion is going to happen over here. Keep on noting down these points. These are very important. Now how the ring expansion is going to happen over here? Let's call this as carbon number 1, this is 2, this is 3, this is 4, this is 5. Simple. Break the 2,3 bond, break the 2,3 bond and make the 1,3 bond. Simple. And whenever you try to do the ring expansion or ring contraction, simply you are going to break 2,3 bond, make 1,3 bond. So break this 2,3 bond, okay? Break this 2,3 bond, right? So basically this 2,3 bond, this should be broken down towards this carbon such that this carbon gets a negative charge, and this negative charge I can attach with this CH2, okay, and finally positive charge comes somewhere here, right? So I'm not going to, you need not to remember all this. You simply will be doing one thing. Simply remember one thing. Just break the 2,3 bond and make the 1,3 bond, right? If I'll break the 2,3 bond, I'll be getting something like this, okay? I mean the ring expansion which I'm showing you over here, it's going to be like this. Since I'm going to break this 2,3 bond and I'm going to make this 1,3 bond, and eventually there'll be a positive charge on this carbon right here at carbon number 2, okay? As simple as that, right? See, this was a 4-membered ring. Now it's 1, 2, 3, 4, 5. Now it's a 5-membered ring, right? Stability has increased. From 4-membered ring, you are getting what? You are getting 5-membered ring due to what? Due to ring expansion. Due to ring expansion, right? After this, I can make this 5-membered ring like this as well. I can directly make it like this, no issues at all, right? This is basically, I can convert it in this way as well, no issues at all, correct? This is my 5-membered ring. Now what is going to happen? Water is going to act as a nucleophile. It is absolutely going to attack at this position, due to which you get the protonated alcohol, and that protonated alcohol that loses H positive, or I can say water takes H positive out from that protonated alcohol, and finally you get a product like this. This is the product which you got over here, correct? Let me know in the chat box if it's clear to everyone, right? Let me know in the chat box if it's clear to every single guy. Fast. Yes. Right? Wonderful. Let's move on. Let me take a few more cases. Okay, what will be the product of this one? Product in this case. First of all, you have got 1, 2, 3, 4, 5. You have got a 5-membered ring, right? Whenever carbocation will be attached with the 4-membered ring or 5-membered ring, at that time, what happens? At that time, ring expansion takes place, okay? So first of all, this is the Sn1 mechanism again, which I'm showing. What you'll be doing is, you'll be simply breaking this bond, so that will be positive charge on this carbon, right? Now this carbocation, it's attached with the 5-membered ring. So what is going to happen? What is going to happen? The ring expansion is going to happen, right? Ring expansion is going to take place. But before ring expansion, let me make it clearly. Let me make the carbocation which got formed over here. Yeah, this is the carbocation which got formed. Now we'll understand. This is carbon number 1, this is 2, this is 3, this is 4, this is 5, this is 6, right? Now, what you'll be doing, since you got to know your carbocation is attached with the 5-membered ring over here, so again, ring expansion is going to take place, yeah? Ring expansion is going to take place. And how to do this ring expansion? Simple. Break the 2-3 bond, make the 1-3 bond. That's it. Break this bond and make this bond, right? See, what I'll be doing, you'll be getting something like this. There'll be a positive charge on this carbon over here, right? I simply broke this 2-3 bond and I made this 1-3 bond. As simple as that, right? So basically, what I got over here, I got a 6-membered ring. This is basically a 6-membered ring. 1, 2, 3, 4, 5, 6. So you got a 6-membered ring like this. Okay, with a positive charge over here, for example. Yeah. Now, after this ring expansion, your H2O, which is a solvent, it's going to act as the nucleophile and it's going to attack at this position. So finally, what do I get? Finally, I get something like this. This is going to be my major product in this case, right? Let me know in the chat box if it is clear till here so that I can talk about a few more examples, yeah? Just let me know in the chat box with some thumbs ups. Let me see exactly if you got it or not, yeah? And do not forget to like the video. Do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking live on this channel, yeah? Okay. I'm sure it's clear till here, yeah? So let me move on to a few more examples. Okay, this is one more important example. Remember, whenever a carbocation is directly involved in the ring, whenever a carbocation is directly involved in a 4-membered ring, for example, at that time ring contraction takes place. Okay, and how it happens, understand. First of all, again, I'm going to show you the Sn1 mechanism over here. So you need to break this bond so that there'll be a positive charge on this carbon over here. Yeah. There is a positive charge on this carbon, right? Now, people, is this positive charge inside this ring? Yes, right? Okay, this positive charge, it's a part of this ring over here, correct? Whenever the positive charge becomes part of this 4-membered ring, remember at that time, what happens? At that time, ring contraction happens, right? Okay, and due to ring contraction, why this ring contraction happens? Because, see, I told you rearrangement only happens in order to increase the stability of carbocation. If I'm telling you ring contraction is going to happen over here, that means you'll be getting a carbocation which will be definitely more stable than this one, yeah? Okay, now we will see how this ring contraction is going to take place. This is carbon number 1, this is 2, this is 3, this is 4. Break the 2-3 bond and make the 1-3 bond. As simple as that, yeah? Break this 2-3 bond and make this 1-3 bond, right? Break this bond and make this bond, right? So finally you get something like this. Have a look. You get something like this. This is CH2 with the positive charge, right? I have broken this 2-3 bond and I have made this 1-3 bond over here. So finally, you got this carbocation, right? This carbocation, I can make it like this as well. Okay, if you remember, it's called as, what do we call this carbocation? Can you let me know fast? What do we call this carbocation? Exactly. It's going to be cyclopropyl methyl carbocation, which is one of the most stable carbocations, right? Okay, now people, again, this cyclopropyl methyl carbocation, okay, this water, which is the solvent, it's going to again act as the nucleophile. So finally what happens? So first step, you're going to get the protonated alcohol, and that protonated alcohol, H positive is lost by that protonated alcohol because water takes that H positive out. So finally you get the product something like this. This is CH2, and with the CH2 you get OH as well. So this is the final product over here. Yeah? Right? I'm sure it's clear to everyone. Yeah? Okay? So people, see, this is something which I've told you, right? So first, carbocation got formed. Whenever the positive charge becomes the part of the four-membered ring, at that time ring contraction takes place. Yeah? So due to ring contraction, what is going to happen? You get this cyclopropyl methyl carbocation, which is one of the most stable carbocations. Yeah? And finally, when this water acts as a nucleophile, when it attacks at this position, finally you get the alcohol over here. Yeah? This is the product. Now people, I've got one question for you. That's something which you'll do at your place, okay? Right? Do let me know the answer of this question in the chat box, and in the comment box, I mean, yeah? Do let me know answer of this question in the comment section. Okay? Do let me know the answer of this question in the comment section afterwards. Right? Okay? So again, in this case, what is going to happen? The positive charge becomes the part of the seven-membered ring. So ring contraction will happen. Right? Okay? I'm sure you'll be getting the answer of this question, and this is your homework. Do let me know the answer of this question in the comment section. Right? Okay, now, let's talk about the factors which affect the rate of Sn1 reaction. Factors on which rate of Sn1 reaction depends. Okay, first of all, the first factor on which the rate of Sn1 reaction depends, that is going to be the substrate structure. What does that mean? See guys, understand. Remember, rate of Sn1 reaction is directly proportional to the stability of carbocation which is formed in the rate determining step. Okay? See guys, first of all, if we talk about the Sn1 reactions, what is my rate determining step? That ionization step in which the carbocation gets formed. That is my rate determining step, right? Okay, so that step basically determines the overall rate of Sn1 reaction. Okay? Now the first case, the rate of that ionization step depends on the stability of carbocation. If the carbocation becomes stable, if during ionization carbocation becomes stable, right, I'll say that step is going to be comparatively fast. If that ionization step is comparatively fast, I'll say overall Sn1 reaction is going to be fast. Okay? Remember from now onwards, the rate of Sn1 reaction is directly proportional to the stability of carbocation formed in the rate determining step, right? See, we have got few examples. Just take this X negative out, there'll be positive charge on this one. Again, take this out, positive charge on this one. Take this out, positive charge on this one, right? See, over here I got 3 degree carbocation, 2 degree carbocation, 1 degree carbocation. 3 degree carbocation is most stable, followed by 2 degree, followed by 1 degree, followed by 0 degree, right? Right? So when I'll be taking this as the substrate, okay, the reactivity of this substrate towards Sn1 will be the maximum. Yeah, because you get the most stable carbocation in the ionization step, right? So if I ask you the order of the reactivity right here is simply going to be tertiary alkyl halide is going to be maximum reactive towards the Sn1 mechanism, followed by 2 degree, followed by 1 degree, right? As simple as that. Okay? Right? I'm sure it's clear to everyone. So reactivity order is going to be 3 degree 3 degree alkyl halide is going to be maximum reactive towards the Sn1. Why? Because 3 degree carbocation leads to the formation of 3 degree carbocation, which is the most stable one. Okay? Which is the most stable one. Yeah? So remember, in short, substrate structure, rate of Sn1 reaction of any substrate is directly proportional to what stability of carbocation formed in rate determining step. Okay? Well, Sai Manju, you can just drag the video a little back. It'll be automatically a replay for you. Okay? Right? Perfect. The second factor on which the rate of Sn1 reaction depends. The presence of pi bond at alpha position with respect to the leaving group. Okay? What it means exactly. What it means exactly. If I talk about something called as vinyl halide, this is the vinyl halide, or you can take the aryl halide as well. This is the example of the vinyl halide. This is the aryl halide over here as well, right? Now people, presence of pi bond at alpha position with respect to the leaving group. What is the leaving group over here? This X is the leaving group, this X is the leaving group, right? So with respect to this leaving group, this is the alpha position, this is the alpha position, right? At the alpha position in both the molecules, you have got pi bond. At the alpha position in both the molecules, you have got pi bond, yeah? Okay. At the alpha positions in both these molecules, you have got a pi bond. Now, presence of pi bond at alpha position with respect to leaving group, what it does exactly? What it does exactly? What it does exactly? Can you let me know in the chat box what happens? Can you let me know fast what happens exactly? See guys, it's a simple case, understand properly. There's a lone pair on this halogen over here, okay? So this is lone pair, this is sigma, this is pi. Can I say over here we have got conjugation? Due to conjugation, this bond will break in this direction, this bond will come in this direction, this bond will break in this direction, due to which this carbon and X bond, it gets a partial double bond character. If it is getting the partial double bond character, what is going to happen to the ionization step? Is that going to be fast or slow? See, you are getting the double bond character. This CX bond is going to be comparatively stronger. So it will be difficult to break the CX bond, right? So the formation of carbocation will take time, right? I can say like that as well. Okay, right? If the formation of carbocation takes time, so I can say your rate determining step becomes the slowest among all. So I can say rate of Sn1 reaction will be less in these two cases, right? As simple as that. Rate of Sn1 reaction, if I'm taking these two as substrates, rate of Sn1 reaction when I'm using these two substrates will be very, very less. Why is that? Why is that? Because you are getting the partial double bond character over here. Similarly, in this case, you are getting the partial double bond character over here, right? It's really difficult to break this CX partial double bond over here, right? So your ionization step, it becomes very slow, due to which the overall rate of Sn1 reaction, when I'm using these two as substrates, that actually becomes very slow, okay? As simple as that, right? Okay. This is something which I told you, rate of Sn1 reaction decreases when I'm using these two as the substrates. So vinyl halide and aryl halides are the cases in which rate of Sn1 reaction decrease when I'll be taking them as the substrates, right? Because of the partial double bond which gets created between this carbon and halogen and between this carbon and halogen, right? Okay, I'm sure it's clear to everyone. I'm moving on to a few more examples. Okay. This is the third factor on which the rate of Sn1 reaction depends. Presence of pi bond at beta position with respect to leaving group. Presence of pi bond at beta position with respect to the leaving group. This X is the leaving group, this X is the leaving group. This is something which I call as allyl halide, this is something which I call as benzyl halide, right? So first of all, with respect to this leaving group, this is alpha carbon, this is beta carbon. With respect to the leaving group, this is alpha carbon, this is beta carbon, right? Now, we have got pi bond at beta carbon in this case, right? See, when X leaves as X negative, can I say there will be positive charge on this alpha carbon, right? When X leaves as X negative, there will be positive charge on this carbon, right? Can I say over here the carbocation which I got formed, okay, it's in conjugation with this pi bond. This is pi sigma carbocation. So it's resonance stabilized. Again, pi sigma and positive charge, right? So again, this carbocation will be resonance stabilized, right? Okay, so the carbocation which is getting formed in this case, which is CH2 double bond, this is CH, it is single bond and it is CH2 positive, right? And in the second case, the carbocation which gets formed is like this. It's like this, right? You have got CH2 with a positive charge right here. Positive charge on both these carbons are resonance stabilized, right? Both the ones are resonance stabilized. So the stability of this carbocation increases and the stability of this carbocation also increases due to conjugation. And if the stability of carbocation increases in the ionization step, what happens? What happens exactly? That ionization step becomes comparatively faster. And if the ionization step comparatively becomes faster, I'll say overall rate of Sn1 reaction when I'll be using these two as substrates, that O actually increases, yeah? So you can clearly say these two carbocations, they are stabilized by the resonance, yeah? As simple as that. Okay? Exactly. Wonderful. So these are the carbocations which I got over here, and these carbocations are stabilized, and more the stability of the carbocation in the ionization step, right? More is going to be the rate of Sn1 reaction when these will be taken as the substrates, right? Okay, so remember in these compounds, the rate towards Sn1 is more because of more stability due to resonance. This was the third factor on which your Sn1 reaction, its rate depends, yeah? Let's move on to a few more examples. Presence of heteroatom at alpha position with respect to leaving group. See guys, this is the leaving group, okay? This is the alpha carbon, alpha position, and this is the heteroatom, yeah? This is the heteroatom, correct? Now people, when this X leaves as X negative, there will be positive charge on this carbon, so you get something like this. This is CH3, this is O with one lone pair and the positive charge, and you get CH2 positive over here. Just a second, what did I do? This is not the positive charge, sorry. This is a lone pair over here, this is positive charge over here on this carbon, yeah? Now people understand. Is the octet of this carbon complete? See, this is the carbocation which I got when this leaving group left over here, right? Okay, I'm simply asking you, this is the carbocation which I got formed in the ionization step, right? Now the point is the octet of this carbon complete? Octet of this carbon is not complete at all, right? Right? Okay. So people, this oxygen, it has got the lone pair. Can I say it can do the back bonding? It can show the back bonding over here, right? It has got the vacant p orbital, right? So this lone pair can show some back bonding. And if back bonding is happening, due to back bonding, the stability of this carbocation also increases. Due to back bonding over here, stability of carbocation also increases, right? Yeah? And if the stability of carbocation increases in the ionization step, rest you know, if I'll use this as the substrate, rate of Sn1 will be eventually more, right? Okay? Musab, you can just drag the video a little back, it'll be a replay for you if you're not getting it, okay? There's an option in YouTube. You can drag the video back, you can watch the replay also, right? Okay, perfect. Perfect, guys. So what happens in this case? What happens in this case? This carbocation is more stable due to what? Due to back bonding, correct? Due to back bonding. Yes. If carbocation stability is more, it's getting increased. That means the rate of Sn1 when this will be using as substrate, it will increase. Yeah. Okay. Now, presence of electron withdrawing group in substrate. Okay. See, this is the substrate which I've taken over here, and this is the group which is basically electron withdrawing group, right? It's electron withdrawing group, correct? Now, if this substrate undergoes Sn1 mechanism over here, what is simply going to happen? This X will leave as X negative. So you get something as CH3. This is single bond. This is C double bond O. This is CH2 with a positive charge, right? This is what? This is your electron withdrawing group. This is your electron withdrawing group. What this electron withdrawing group does? It will increase the intensity of positive charge on this carbon, right? It will increase the intensity of this positive charge on this carbon. Electron withdrawing group will increase the positive charge on this carbocation, right? So this electron withdrawing group, it will destabilize. It will destabilize the carbocation. If the carbocation gets destabilized, what is going to happen to the rate of reaction when this is taken as the substrate? I'll say rate of reaction towards Sn1 will decrease if this is taken as the substrate, right? Okay, I'm sure it's clear to everyone, right? So whenever you have got electron withdrawing group attached, right, that electron withdrawing group, what it does simply is, it simply increases the positive charge intensity on the carbocation, due to which stability of carbocation decreases. And if the stability of carbocation decreases, what happens because of that? I told you, rate of any substrate towards Sn1 reaction is directly proportional to stability of carbocation. And if the stability of carbocation decreases, If the stability of carbocation decreases, rate of this substrate towards Sn1 mechanism, it also decreases. As simple as that, yeah? Okay, so electron withdrawing group, it decreases the stability of carbocation, hence the rate of reaction towards Sn1, it also decreases, right? Perfect. Perfect. The last point, that is the effect of solvent, okay? See guys, in all the cases, I have taken the solvent as water, if you remember. You can take alcohol as well, ROH as well. Simply, you have to take a polar protic solvent. You have to take that solvent which has got very high dielectric constant, okay? And that solvent which has got very high dielectric constant, that has got strong tendency to weaken the force of attraction between the carbon and the halogen, right? As simple as that. Remember, your rate of Sn1 reaction is directly proportional to dielectric constant of solvent. More the dielectric constant of solvent, more is the tendency of solvent to ionize your CX bond, to polarize your CX bond, or you can say like this. More the dielectric constant of solvent, more is the tendency of the solvent to weaken the force of attraction between carbon and halogen, right? Due to which carbocation gets formed easily. If carbocation gets formed easily, I can simply say, since that step in which carbocation is formed, that is the rate determining step. If the carbocation is getting formed easily, you can clearly say rate of Sn1 reaction increases, right? Yes? Okay. In general, your polar protic solvents, like water, like alcohol, which have got very high dielectric constants, those polar protic solvents, they actually favor your Sn1 reactions, okay? The last factor in which your rate of Sn1 reaction depends, that is the effect of leaving group, right? Okay, remember the leaving ability of I negative is maximum, followed by Cl negative, followed by Br negative, followed by Cl negative, followed by F negative. The leaving ability of I negative is maximum, followed by your Br negative, followed by Cl negative, followed by F negative, right? And rate of Sn1, it's directly proportional to the leaving ability of the group. For example, I've taken 3 cases over here, right? I need to see, arrange in the decreasing order of the reactivity towards Sn1. Arrange the following in the order of decreasing reactivity towards Sn1. So first of all, you're going to break this bond, break this bond, break this bond. This iodine will leave as I negative, this Br will leave as Br negative, Cl will leave as Cl negative, right? Carbocation everywhere is same. It is a 3-degree carbocation. So you cannot decide the reactivity on the basis of the stability of carbocation over here, because the carbocation everywhere is same. But over here you have got the leaving group as I negative, Br negative, Cl negative, right? And as I told you, what? Rate towards Sn1 is directly proportional to the leaving ability, and leaving ability of I negative is maximum, followed by Br negative, followed by Cl negative. So this one is going to be maximum reactive, followed by this one, right? So 1, 2, 3 is going to be the decreasing order of reactivity in this case over here, right? I'm sure it's clear, right? Okay, one more factor. Okay, one more factor on which your rate towards Sn1 reaction depends. Remember, rate towards Sn1 reaction is enhanced in presence of Lewis acid or ionic salts or cations. What it means exactly? See guys, understand. I've taken 2 cases. Over here we have taken alkyl halide. This is also the alkyl halide, right? This alkyl halide, I have taken it in the pure polar protic solvent, right? It's going to follow the Sn1. Now, same thing I'm going to do in presence of either Ag positive or AgNO3 or BF3, right? Now, let's assume rate of this reaction is R1. Let's assume rate of this reaction is R2. Remember, R2 is going to be greater than that of R1. What is the reason for that? See, if I take any one of these two, see, this halogen has got the lone pairs, right? You know it, right? So this lone pair, it can donate to this BF3 because boron is electron deficient center. Its octet is not complete. If it donates this lone pair in the form of coordinate bond to this BF3, there'll be positive charge on this halogen, right? And positive charge on electronegative element makes it more electronegative, due to which this bond is broken down easily, right? And if this bond gets broken down easily, carbocation gets generated easily. And once the carbocation gets generated easily, I can clearly say rate of Sn1 will increase. Yes. Right? I'm sure it's Clear till here, right? Okay, now this is something stereochemistry of Sn1 and Sn2 reactions. I'll be taking a separate session for it, right? I'm not going to talk about the stereochemistry of Sn1 right now because I've not taught you what is RS nomenclature, right? I've not taught you that, those configurations, inversions, retentions, racemic mixture. That's something which I'll be teaching you in the isomerism, right? The optical isomerism, right? And after that, I'll be covering the stereochemistry of Sn1 and Sn2 in a separate session. Okay, so people, this is something which I'll be teaching you in the coming session, right? So before ending the session, for the ones who have not joined in into the NEET 2021 crash course yet, please do join in to the NEET 2021 crash course. Well, in this crash course, this is the best and the last option which you guys have in order to improve your ranks for the NEET 2021 examination. Just do one thing. Okay, let me first of all tell you what all things we are going to cover over here. We are going to cover your whole syllabus in just 120 sessions, right? No need to worry about the assignments, no need to worry about test series, no need to worry about the mock tests. Everything is included right here. Yeah? Okay, and people, at the same time, it's going to be a two-way learning interactive platform wherein you can ask your doubts anytime to your master teachers, right? Okay, and there will be some amazing tips and tricks by means of which you can solve the questions in lesser time, right? How to get enrolled in this, how to get enrolled in the NEET 2021 crash course batch. What you need to do is you need to download the Vedantu app. After downloading the Vedantu app, just click on the NEET crash course, and after clicking on the NEET crash course, do not forget to use this coupon code as WSNET. After using this coupon code, you'll be getting some 30% off as well, and I'll be training you personally in this NEET 2021 crash course, which will happen on the actual Vedantu platform. The next batch is starting on 14th of June. Do get enrolled in it as soon as possible. Link is there in the description box of the video as well. You can click on the link, get added, right? Okay, you've got two options of getting added over here. The link, either by clicking on the link using the coupon code or downloading the Vedantu app. Choice is all yours, right? And there is one more link in the description box of the video. That's for the Telegram. Do click on the link, get added to the Telegram group, and stay updated about the classes. And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. Well, this was about Sn1 reactions. In the next session of this alkyl halides, we'll be doing the Sn2 reactions. Okay, I'm sure everything is clear till here. So let's meet up tomorrow at the same time. Till then, you take care. Bye-bye. God bless you all. And people, one more thing I would like to share with you. I have started the atomic structure for NEET 2023 batch. Okay, you can join in to cover that chapter in the 2023 batch. Yeah. Okay, so that 2 chapters will parallelly go on. The timing for the tomorrow's session will be, I guess, either at 10:30 a.m. or at 7 p.m. Right? Okay, just check the community section after some time. Chalo, I'll take a leave. See you guys tomorrow. Bye-bye. Bye guys. Take care.